we've thought about vector flux through a uniform surface. So to introduce the idea, we had the easiest case, a uniform field and a uniform surface. And by that I just mean a flat surface where you have a nice single area vector like that. But of course, we have to move on to more complicated things. We have to look at a non-uniform surface and see how do we calculate the vector flux for that. So let's erase our nice, convenient, pretty little uniform surface and imagine we have some curved thing, some complicated curved object like that. This gets a little bit tricky because what is A? Right? The A vector could point all different directions. You've got to know how to figure out what A is. So this is similar to something you're actually already familiar with, and that is this is a disco ball. So this is the Hertzian Amphitheater disco ball. We only bring it out in special occasions such as this. And you can see it's a curved spherical surface, but it's covered in these little square tiles. So this is the idea. You take your complex or your complicated curved surface and you cover it with small simple surfaces that you could define as having their own little area elements. You can imagine the area coming off each one of these mirrors, and on this side they stick out this way, and on this side they stick out this way. But all together they make the curved surface that you need. So that's what we're going to do here. We are going to think about this complex surface, and we're going to break it up into little strips that make a bunch of little squares like that. Oh, not perfect, but you get the idea. And then we can think about the little area of each one of these small squares like that. Now the only complication is how do you calculate the flux from this complicated object? We know what to do in terms of tiling it. We break the surface into small squares, but then what do we need to do? We have to sum them up. And since you know that that's an S and an integral sign, you know what we're going to do. We're going to calculate our flux not as just a dot product, but an integral of a dot product. So phi E, the electric field flux, usually it's E dot A, but here we're going to think of each one of these as a dA, a little differential unit of area. So E dot dA, and then we just add that flux up over the whole area. Okay? So it's another case of integration that you have to think about. What can get tricky is two things. It can become complicated because dA varies in space. As you move around, the direction of dA depends on where you are. And E might vary in space. We may do cases where E is not just a uniform field. So E can vary. Maybe you'll have a curved surface and a point charge with the E field pointing all different directions. So when you get into this kind of integral, with everything varying, that is a scary thing known as vector calculus. And you can imagine the integrals can get difficult. And that's why it's an entire high-level math class. What we do in freshman physics is we have to understand the idea of vector calculus. You have to have in your head and understand what this means in terms of disco balls and fields. But we aren't going to do the really hard integrals. We will always use symmetry to make the integrals more manageable.